of India, but I think ISI can still be given the credit of taking the lead in most of the activities here. So Dr. Mukesh Prasad, uh, as I told you, is a senior faculty member at the University of Technology, Sydney. And I don't know, I think Dr. Jyoti Singh would tell you at some point of time, he has a master's degree from JNU, from where
Yes,
Jyoti
sir.
also comes, right?
Yes, sir.
And then after his master's degree, I just learned that he moved to Taiwan for his PhD. Then he also worked in industry there. And now he is in Australia, and he happens to be a core member of very prestigious Australian Artificial Intelligence Institute, right? So I'm sure that we have a very distinguished speaker today in Dr. Mukesh Prasad. And without taking much of your time, I welcome him once again and invite him to deliver his talk.
Thank you
Dr.
so
Mukesh
much, sir.
Prasad.
Yes, so Dr. Mukesh, over to you, sir.
Can you see my screen?
Yes, sir. Yes, we can see it.
Okay. Can you see the slides?
Not yet, sir.
Not yet, not yet, not yet.
There is some issue.
Yes, 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 yes. Oh, yes.
Can you see now?
Yes,
Yes.
we can see it.
Okay. Good afternoon, everyone. Sorry for being little late because I had some issue with my the previous laptop and the camera was not working. First of all, I would like to thank Dr. Jyoti for her invitation to giving a DST series lecture on the topic of fuzzy logic and the neural network. And also, I would like to thanks Professor Arun Srivastav for his initial introduction about me and the topic itself. And also, I would like to all participant for your time to attending and allow me to introduce the topic. So fuzzy logic and the neural network itself is a very big topic. It's not going to cover in even in a 1 week or 1 month. So what I did, so I just capture one very specific topic and its application towards the neural network. So today I'm going to talk on the one of the part of the fuzzy logic that's called fuzzy C-mean clustering. So the technique which I'm going to talk on the collaborative fuzzy clustering and its application. So when I say this application, so we can apply the fuzzy this collaborative fuzzy clustering into many different areas wherever it's applicable. So the example I'm going to show, it's more about the fuzzy neural network and the Tajagi-Shukrino models and so on. And we will go through the couple of examples how it can be beneficial to solve a real world problem. So let me introduce myself first. So I'm a senior lecturer at the School of Computer Science, Faculty of Engineering and IT at University of Technology, Technology, Sydney. Also, I'm a core member of the Australian Institute of Artificial Intelligence. So, Australian Institute of Artificial Intelligence, Australia number one. Around the world. Every year, this is a very young university and it's growing day by day. It's because of the contribution and hard work by the academic and the researcher. Okay, so before joining the University of Technology Sydney, yeah, so I did my PhD from National Chao Tong University in Hsinchu. Hsinchu is one of the industrial hub in Taiwan. And yeah, and then after my PhD, I work with the world's biggest manufacturing company. That's a semiconductor company called Taiwan Semiconductor Manufacturing Company. And I worked there for 1 year, and then I moved to Sydney in 2017, joined as a lecturer, and then I promoted to senior lecturer and so on. So before moving to Taiwan, I did my master MCA of the School of Computer System and Sciences. I think where Dr. Did also a PhD under the supervision of Dr. R.K. Agrawal. So Dr. Agrawal, one of my favorite teacher there. Okay, so basically I born and brought up in Bihar, and where I did my all basic study till undergraduate, and then I moved to Delhi. After I finished my MCA, I worked as a software engineer for 1 year, and during so it was in 2009. Then when the recession hit, then I decided to continue my higher study because was a job issue and so on. Then I got a scholarship, and then I started my PhD. Okay, so this is just a brief journey of my whole career till now. Okay, so today what we are going to talk. So today I'm going to talk the motivation behind this research topic, and give a brief introduction of the fuzzy C-mean clustering. Then I'll talk about the collaborative fuzzy clustering. Then I talk the improve or on different variant of the collaborative fuzzy clustering. That's the pre-processed collaborative fuzzy clustering. Then we will see how we can use the collaborative fuzzy clustering with the neural interface networks, where I'll talk a bit of the neural fuzzy inference network and the proposed work, and then experimental results. And further, we will talk on the other models such as the Mamdani and the Takashi Subuno Kang, that's also called TSK type model, with the collaborative fuzzy clustering. And then I'll talk on the proposed model, experimental results, and then the conclusion. Okay, so the main motivation behind this research topic nowadays, I think this is the big challenge in recent year, or it's been since many years, about the sharing the information of the customer or the any organization. So we can't share because of the privacy and security issues. So, but there are a different way we can again we can share the information of the customer or particular person through the other organization. So the idea is why we need to share the information to the other organization, because let's say we want to improve the sales of our particular product, but we need to get the information about the customer, its behavior. but again, we can't share it directly, because of the privacy and security issue. So there are many different ways we can share the particular person information without revealing their actual, information. So, of course, we need to share the information. We want to promote our product. We want to get a better inside information, which can help us to deal with some particular problem. So yeah, so there is a need where we need to share the information while keeping the privacy and security issue of particular databases. So sharing the information, let's say you want to share the information of a particular patient with another hospital, but again, it's due to the privacy concern we can't share. So we need to develop such system which can help us to share and improve the quality of the care of particular patient as well, or it can also help us to predict or do some classification of the particular disease based on the historical data and the information of the patient. So yeah, so there is a need of sharing the information in order to improve the quality of the service and so on. Also recently, big data analytics and the transfer learning are the two major research focus for the industries or research organization in the field of engineering, bioinformatics, and the social media or finance forecasting. So yeah, also sharing the big data is not easy, and also through the transfer learning, we can easily transfer the features of the particular databases, which can again help organization to improve their quality of the service or the care in area of the healthcare services. Yeah, so the technique which is going to help to deal with the big data analytics in terms of the volume. So instead of sharing the whole data, this technique will help to share the information of the a small portion of the data set, and that's a good enough for the information on the whole data set. So later we'll talk how we can reduce the volume of the data set if you want to work with the big data analytics with the fuzzy C-mean clusterings. And also yeah, so this proposed method also can be applied to improve the performance of the system in terms of the learning ability, because when you have the large data set, usually the computation time is a mainly concern of any of the organization or the particular system. So instead of using the whole amount of data set, you can use the small portion of data sets that's even going to work and give you the similar performance on the small data set itself. Yeah, so this is just a very basic definition of the fuzzy C-mean clustering. So before I'm going to talk about the fuzzy C-mean clustering, I will just give you a basic idea. So fuzzy C-mean clustering is a part of the unsupervised learning, so of the machine learning. So in machine learning, basically we have two types of the learning. First is a supervised machine learning technique and the unsupervised machine learning technique. So with the supervised machine learning technique, usually we do kind of classification or prediction. There are a lot many techniques involved, such as the decision tree, random forest, support vector machine, k-nearest neighbor, naive bias, and so on. So we are not going to talk in that direction in the supervised learning. We are going to focus more on the unsupervised learning. So even in the unsupervised learning, we have a different approaches. So clustering is one of the part of the unsupervised learning. There are other techniques such as association rule mining. That's another techniques part of the unsupervised machine learning. Even in the in the clustering, we have two kind of clustering. The first is your first is the hard clustering, and second is the soft clustering. So hard clustering means when you do the clustering, that's the particular object just belong to one particular clusters. But with the soft clustering, so fuzzy seaming clustering is a part of the soft clustering. That means in soft clustering, usually one data points can belong to more than one cluster. So it can share some kind of feature with the other clusters as well. That's why it's define a membership value. So membership value, so one particular object, when you develop the cluster, so one particular object has a different membership values, and that membership value define whether it's belong to which cluster. So fuzzy seaming clustering basically it's introduced by Benjack in 1981, and so it's allow each data points exhibits to one or more cluster that are specified by the membership function. So I just discussed. So the main objective for fuzzy seaming clustering is to minimize the following objective functions. So with this objective function, we are going to look for the clusters, and based on the given data set, we are going to optimize this function, which can give us the centroid and the membership value. So so the whole idea behind this fuzzy seaming clustering to optimize this objective function to get the centroid and the membership value. So we can see so the UIJ is a degree of membership value of the particular data points, and for the cluster J, so J is the number of the clusters, where C is the number of the cluster, and J start from 1 to C, and Xi is the highest data point of the d-dimensional data set, and Vj is the dimension of the cluster, and this is a normal expression. Actually, it's calculate the similarity between. So that's basically the distance between the two distance between the data point and the cluster. So there are different methods to calculate the distance. So one of the common methods usually we use the Euclidean distance. I think if you guys have taken the fuzzy logic, and so you know the how to calculate the distance between object and the centroid. Yeah. So okay. So next. So these are the just steps of the whole fuzzy seaming clustering. So first we need to set up the number of the cluster. So number of cluster basically is a user defined. So you need to define the value of the cluster. So once the value of the cluster defined, then we need to select the basically select the initial cluster prototype that's based on the number of clusters. So let's say there are 3 different clusters, so there will be a 3 different prototype, and for each prototype based on the data's given data points, and then we compute the distance between the data point and the each clusters, and so once you calculate the distance, then now you need to compute the partition matrix. So partition matrix basically define the membership value. So this is the equation you need to use to compute the partition matrix. And then once you compute the partition matrix, then we need to update the centroid accordingly based on the computed partition matrix of particular data point. So this is how we can update the prototype, and then there are some stop criteria we need to define. So stop criteria is based on the convergence to attend. So if and also you can define the number of iteration. So if number of iteration exceed the given value, then it will automatically stop. Otherwise, then we go on the repetition, which is a start from the step 3. So again, we'll compute the distance for the next value with the prototype, and then it will goes on. So this is the kind of iterative process we need to usually do in the. So if you look at this step, it looks very simple, but when you implement it, require a bit of logic behind it when you start coding. But nowadays, you don't need to worry too much on the coding. There are lots of library exist even in Python or R if you are familiar with. So you just call the library and provide your data set and give the number of the cluster, and then you will have the final result. So you don't need to worry too much. If you're just thinking to apply the fuzzy C-mean clustering, you can apply. But if you want to know more theoretical part, you need to have some basic mathematics background, and also you need to know some optimization technique as well. Then only you will be able to implement or do some modification in the existing methods, and then you can compare your proposed methods with the with the FCM. So that's more on the research side. Okay, so this is just an example of the fuzzy C-mean clustering. So this is the scatter plot of the given data set. So you can see this is how the data sets looks like. So when you perform the fuzzy C-mean clustering, so you can see at the bottom left, it's represent the fuzzy C-mean clustering for two clusters. So you can see the green circle represent the one clusters, and the red plus data points represent the second clusters. And this dark black circle represent the centroid of these clusters, and then the plus dark represent the centroid of this cluster. And this is your objective functions, how the learning curve, the objective function. You can see, so even let's say the maximum number of iteration was defined is the 30, but you can see there we have the another criteria, that's the convergence rate. So you can define some convergence rate. So if convergence rate stop converging, so it will automatically terminate the program. So you can see after, it seems like after 20 iteration, the convergence has become steady. So that's why the whole program will be executed, and then it will give you the outcome, what you can see at the left bottom side. So this is another example. So instead of using the two number of cluster, now we can see this is example for the 3 different number of clusters, and this is just a example of how the convergence rate. So in this case, you can see the convergence rates has gone. The number of iteration is more than 50. And this is another example when you use, so it's the same data set, but we are using the different number of clusters. So now we are using the four number of clusters. So you can see how the clusters behave. So, and then you can see we have 4 different of clusters, and this is how the objectives, the convergence graphs looks like. Now we will talk about the collaborative fuzzy clustering. So why we need to use or introduce collaborative fuzzy clustering, and why it has been introduced. So the only thing is with fuzzy C-mean clustering, it's only suitable to handle only one data set. So if we have more than one data set, so we need some other approach which can deal with. So that's why we proposed the collaborative fuzzy C-mean clustering to reveal the structure being common or similar in the number of subsets. So let's say you have 2 different data sets, and so collaborative clustering can help us to to find the what are the common or similar structure on the given data sets, and then it uses the features of the those common structure, and then collaborate each other, and then update their information, and then they share the whole information to the other data set. So how it works. So let's say two different organizations have a data set, and they want to share the information. So how they are going to share the information? So they need to perform the clustering algorithm locally. That means they are going to perform the clustering algorithm on their individual data sets. So once they perform, so they will just have the information in terms of the centroid as well as the partition matrix and the centroid. So once you generate the centroid and the partition matrix, then it's give the information in the kind of translated information that's not the real information of the particular data point. So and then they can collaborate globally, so they can exchange the information with the partition matrix and the prototype. So in that case, they can preserve the confidentiality of the data as well as the security problem. Yeah. So they don't need to share the whole data set. They just apply the individual apply the algorithms on their own data set, and then that algorithm help them to create the centroid and the partition matrix, and then they share those centroid and partition matrix to the other organization, because the way centroid and partition matrix works is just some numeric value, so it's not the actual information which data set has. So in that case, they will preserve the privacy and security issues. Okay, so basically there are two ways to perform the collaborative fuzzy clustering. The first one is called the horizontal collaborative fuzzy clustering. So we have a different type of data set and with the different functionality or dimension. So some data set, let's say two organizations have a data set which has the similar features, but the number of sample is different. And some organization, they have this same number of samples, but the different features. So that's why we need to adopt the appropriate collaborative fuzzy the clustering. So when we need to apply horizontal collaborative clustering, so when you have the same patterns but the different features, so then in that case you can apply the horizontal collaborative clustering. When you have the different pattern but the same features space, then you can apply the collaborative the vertical collaborative fuzzy clusterings. At the bottom figure just represent how these schemes works, the collaborative fuzzy clustering. So let's say you have so this is just an example of the two data sets. So if you have a multiple data set, you can apply the same mechanism that's going to work. So this is just an example of two different data sets. So let's say we have a data set L and data set M, and so each data set they are going to apply the techniques, the algorithm. Then they will calculate the prototype, that's a centroid, and then they will calculate the membership value, that's called the partition matrix in terms of the collaborative fuzzy clustering. So each individual data set locally, they will compute their partition matrix and the prototype. So you can see, so this is a partition matrix and prototype for data set M. And this is the way how they're going to compute. So where the beta basically define the strength or the strength of the collaboration. So again, Beta is a user defined, so you need to define the beta that the value is greater than 0. So beta M and L, that means the data set M is going to collaborate with data set L. Beta, L, and M represent when the data set L is going to collaborate M. So how it works? So when the data set M collaborate with data set L, that means so whatever feature or information involved in terms of the partition matrix and prototype for data set L, then based on this information, so data set M in terms of the partition matrix and prototype, it will update its own partition matrix and the prototype. So when data set L collaborate with data set M, so data set L will update its information of the partition matrix and prototype based on the given information of the data set M. So this is just notation how you can basically describe when you define beta M and L and beta L and M. Okay. So if you remember the objective function of the SPM, so the first the circle is this is the original objective function of the SPM, and now when you talk about the collaborative fuzzy clustering, so we need to define the new objective function. So the add-on to the original FCM is the the word circle. So beta is your user defined. That's define the extent of the collaboration, and this is L and M. That's the collaboration between the data set L and M. And how and again, so they are going to update their information. So you need to compute the kind of it's again the distance matrix between each partition matrix, and then again this is the distance of the data set L. So this will vary. So when you change the beta ML, then it will become d square IJM. So it depends on which data is going to collaborate with which data set. So based on the information, we need to update this one. So this is the objective function we are going to optimize in order to get the updated partition matrix and the prototype. So this is how, so once you optimize this objective function, later I'll show you the steps, what are the steps involved in order to update this partition matrix and the prototype. So this is how your updated prototypes looks like. And this is, this is the partition matrix, and this is the updated prototype. So let me just explain the steps that's involved. So basically, as I said, so this is our the objective function which are going to optimize. So we are going to use the Lagrange multiplier techniques to optimize this objective function. So how to optimize this objective function to make the partition matrix in order to constant free optimization. Then we need to define the lambda, and then so this is the way we are defining, where lambda is the represent the Lagrange multiplier. So once you optimize this objective function, so you can see you need to do the differentiation with respect to the data sets, and again with respect to the Lagrange multiplier. So once you use these two differentiation functions, then you will have the if you're good with differentiation, you will be able to understand the whole process. So we need to do the differentiation for the with this objective function, and then after you doing some few steps, you will be able to get the final updated version of the partition matrix, which is calculated here. Similarly, for this, so once you have the updated partition matrix, so these are the equation we are going to use to finally define the and replace the Lagrange multiplier with the given value. So once you put this Lagrange multiplier here, and then you will have the this one is the your final updated partition matrix. So once you have the partition matrix, now we need to again update the prototype, that the centroid. So again, we need to use these Lagrange multiplier techniques to update the prototype of the particular algorithm. So after doing a couple of steps, you will be able to come up with this updated prototype value. I know this is a bit complicated. It's not easy to understand, but if you follow these steps, you will be able to understand easily. And so these are the just steps of the collaborative fuzzy clustering. So you can see, the step one is basically your fuzzy C-mean clustering. And the step two has been added with the following approach. So first you need to define the collaborative link, that's the value of the beta, and then you can compute the updated prototype and the updated partition matrix using the equation 1.9 and 1.12, which we discussed before. And then, yeah. So this is the just pseudo code of the whole collaborative fuzzy clustering. So this is some visual representation how the collaborative fuzzy clustering works. So let's say this is the scatter plot of the two given data sets. So this is data set 1 and this is your data set 2. And when you perform the individual clustering techniques on the each data set, so how the clusters looks like. So you can, let's see, these are the 3 different clusters, and data set 2 has the another different cluster. So when you perform the collaborative fuzzy clustering, then you will be able to see the changes in the structure of the cluster. So for this collaboration scheme, we chose a beta is equal to 0.5. So once you can see, once the collaboration happened, so you can see how the structure has been changed after the collaboration. So you can see, so basically, so after the when the dataset 2 collaborate with dataset 1 collaborate with dataset 2, you can see there is some changes. So before the data point 4 and 5 was belong to this cluster, but now after the collaboration, you can see now the data point 4 and 5 now it's belong to this cluster. So you can see these 4 and 5 created a different cluster. So you can see, but data point 9 and 10 is remain with this cluster. Data points 1, 7, 8 is remain in the cluster, but it's added the another data points from from this cluster. So you can see there is some changes in the structure of the cluster. Similarly, we can see there is some changes in the structure of these clusters as well. Before, you can see these whole data points were belong to this cluster, but after the collaboration, now we can see the data points, especially 4 and 5, and now it's belong to they form another cluster. So you can see, yes, there are some changes in the structure of the cluster based on the what information this particular data points. But again, we can't say whether the change in the structure is a valid or not. So we need to find some way to validate the clusters, whether there is an improvement or the clusters and so on, whether the change structure is valid or not. So there are some techniques we can apply to validate the cluster. So there are two ways to validate the cluster. So first one is called the partition coefficient, and second one is called classification entropy. So you can use these two techniques to validate our cluster. So when we apply these two techniques, we can see, so this is the data set 1 and data set 2, and this is the result when we define the beta is equal to 0.2, and this is the partition coefficient and the classification entropy. This one is the before collaboration for data set 1, and this is the before collaboration data set 2. And this is the result of the partition coefficient and the classification entropy after the collaboration. So if the value is close to 1, so that means that cluster is a good clusters, and if the classification entropy is close to 0, that means that particular cluster is a valid cluster, or we can say it's a good clusters. So of course, whenever we apply some technique, we need to find some way to validate whether it's appropriate or no. We can't just blindly say, okay, based on the structure of changing in the clusters, okay, this method is going to work. So that's totally wrong. Okay, so also we can see in terms of the partition matrix. So this is the partition matrix for the data set 1, and this is the partition matrix for data set 2. So when you do collaboration, we can see easily there are some changes in the partition matrix of data set 1 after the collaboration, and similarly there are some changes in the partition matrix of the data set 2. And again, this is just another way to represent to see what are the changes in the prototype. So this is, you can say this is a prototype, or you can say the centroid of the clusters before collaboration for dataset 1, and this is a prototype of the dataset 2. So you can see there are 3 different clusters here. So you can see that also there is a shift of the centroid of the clusters after the collaboration for dataset 1. And again, there is I can see there is a shift in the clusters after the collaboration here. Okay, so again, there is some issue with the collaborative fuzzy clustering. So further, we propose the pre-processed collaborative fuzzy clustering. Because when we apply when you take the difference between the matrices, especially for the partition matrix of dataset L and dataset M, so the whole idea is to, we lost the useful information under the different partition matrix of the one partition X cluster. So when you look at the information, okay. I'll show you. So yeah, so when you do the basic clusterings here, you can see all the time this color, the color notations always change. So when you run next time, you may not get the same structure of the cluster. So might be the green comes somewhere, the red become green and green become red, and or the blue become green or red. So we need to fix that issue before taking the difference between the 2 different clusters. That's why we propose some pre-processed techniques that can help us to look at the look at the exact information which we are going to compute the distance. So sometime what happened, as I said, the cluster defined in the kth rows may different from the one described in the kth row after the collaboration. So we need to make sure and align with that party exact information. That's why we need to do some pre-processing before feeding to the collaborative for this in clustering. So this is just an example. So let's say you have the original data set, then you divide that data set, a big data set, into a small chunk. So if you say data set 1, data set 2, or data set n. So on the bottom left diagram represent when you do the collaboration of data set 1 and data set 2. So when you perform the clustering locally on the individual data set, so this is how the clusters look like: cluster 1, cluster 2, and cluster n. When you perform the clustering of the data set 2, so cluster can be different. So maybe cluster n, cluster 3, cluster 2. But now when you perform the collaborative clustering, you need to take the difference, this distance between the cluster 1 to cluster n. That's not the right. So we need to find some way where you can find the right clusters of the data set 2 as well. So that's why we need to perform the pre-processing. So after the pre-processing, what you can see now, so you can see, so we have the cluster 1, cluster 2, and so on. And then after the pre-processing, you can see there is a changes in the structure of the cluster. So you can see it's now is aligned with the structure of the data set 1 as well. So now it's more convenient or right way to take the difference of the cluster 1 and cluster 2, and then cluster 2 to cluster 2, and cluster n to cluster n. Again, we need to validate whether the cluster is appropriate or no. So we can see so how to validate what we did. So this is as I mentioned previously. So you can see. So this is just an example of the clusters. So you can see. So when you perform the clustering for 3 different clusters, this is a structure. And so this is for the data set 1, and this is your cluster performed locally for data set 2. So you can see the difference. So if you want to take a difference, so you can't just take a difference for this cluster to this, because now the cluster has been shifted in data set 2 to here. So you can't take a difference between this cluster to this cluster. You need to take a difference. But with the program, we need to find some way to adjust this information. So once you once you apply the pre-process techniques, so you can see after mapping. So we need to map to this cluster with the data set cluster 2. So after mapping, we can see there is a changes in the structure of the cluster. So now you can see this one is the blue, and this green and red. Now we can take a difference of these 2 different clusters easily. So now you can see the after the mapping, the clusters structure of data set 1 has been changed here. So we just need to change the structure of the only one data set based on the information of the other data set. So now you can see it's easy to take the difference between this cluster and this cluster, this cluster and this cluster, and that. So now it's aligned to each other. So there is no misinformation of when you perform the clustering. So also again, we need to validate. So later I will show you the validate, how we did validation. So again, so we added another phase on the collaborative fuzzy clustering. That's called phase 2. So phase 1 and phase 2 remain the same. We just need to add another phase before putting in the collaborative fuzzy clustering. So we need to compute the minimum distance between the centroid and so accordingly we can update the information of the centroid of the one of the data set. So this is the equation we can use to update the information of the centroid of the particular given data set. So now we need to validate. So there is a way to validate called degree of approximation. So degree of approximation helps the measure the similarity. So that means if the value of this is a smaller, that means that particular clusters are more similar to each other. So accordingly, we can see. So this is the table 1 and table 2. So we use two different data set to perform the degree of approximation, just to see the behavior of the clusters with pre-processing and without pre-processing. So you can see the delta one evaluates the similarity of the partition matrix before collaboration. Delta 2 represent the similarity of the partition matrix after collaboration, but this one is without pre-processing, and delta 3 is after the pre-processing with the collaborative fuzzy Seaman clustering. So you can see we use a different value of the beta to just see which one is going to perform better on what value. So we perform the degree of approximation. So you can see the value. And so as I said, the smaller value, that means represent the higher degree of approximation. That means that particular cluster is more similar to the other cluster. So you can see, yes. So you can see now there is some changes in the degree of approximation. So by this way we can see, okay, yeah. So this method is working properly. Okay, so this is another example of the pre-process collaborative fuzzy clustering. So you can see, so this is your original scatter plot of the given data set, and now you perform the. So this is just an example of data set 1. Now you perform the fuzzy Seaman clustering on the data set 1, and this one is your when the dataset 1 collaborate with the dataset 2. So this is how the structure, you can see there is a shift between the structure, but again you can see when you perform the collaborative fuzzy clustering of dataset 1 with dataset 2, you can see there is a changes in the structure of the cluster. So now we need to align with this one. So now when you perform the pre-process technique, then you can see now the clusters align, and also you can see after the collaboration, you can see there is some changes. There is a shift in the centroid as well as the partition matrix as well. Yeah. So you can see after the collaboration, this particular data points, that's the blue one. Before it was belonging to the green cluster, but now it's belong to the blue cluster. So you can see there is some changes in the structure with the in the cluster itself after the collaboration and with the pre-process techniques. Similarly, you can see, so this is just an example of the dataset 2. When the dataset 2 collaborate with dataset 1, you can say this. So this is output of the collaborative fuzzy clustering of dataset 2, and now you can see this is the structure of the cluster performing the pre-process technique. Yeah, with the pre-process technique. along with the collaborative fuzzy clustering for dataset 2. So you can see, yes, so it's going to work. And similarly, we can see there are some changes of the overall partition matrix. So you can see the partition matrix. This one is a partition matrix before collaboration. This one is a partition matrix after collaboration, and this one is a partition matrix after collaboration with the pre-process. So you can, if you look at the data, so you can see the partition matrix here before collaboration 0.95 and having changed to. So there must be something wrong here. So with the pre-processing, you can see now it can align with the original information here. So of course, I think we need to do some pre-processing. So this result is based on the collaborative coefficient 0.5, and similarly you can see there is a changes in the partition matrix of the dataset 2. So this value is the before collaboration, this is after collaboration, and this one is the after collaboration with the pre-process technique. So you can see there is some changes in the structure of the partition matrix as well. And again, this is just again there's changes. We can see there's changes in the structure of the prototype as well. So you can see this is the prototype before collaboration, this is a prototype after collaboration, and this is the prototype after collaboration with the pre-process technique. So you can see again, this is the whole value has been calculated for the beta is equal to 0.5. Okay, so this is what all about the collaborative fuzzy clusterings and the pre-process collaborative fuzzy clustering. Is there any question till now? Yeah, if I'm going a bit fast, please stop me and just let me know. Yeah. Is there any question?
So in K-mean clustering and fuzzy C-mean clustering, which one is optimal?
Yeah, so both has the different functionality. So as I say, K-mean clustering is your hard clustering, and fuzzy C-mean clustering is your soft clustering. So K-mean clustering, of course, in terms of the optimality, in terms of the structure of the cluster, again, we need to validate it. Is totally depend on the given data set. So we can't say, okay, fuzzy C-mean clustering is optimal for all given data sets. So there is a theory we called there is no free lunch. So that means we can't complain that okay, one particular technique is going to work for all given data sets. So it's vary. So we need to try both. Okay, and then you can validate the cluster, and then you can compare and see, okay, this cluster is going to perform better and so on. So, in terms of the computation, yes, so in terms of the computation time, K-mean clustering is faster than the fuzzy C-mean clustering. But in terms of the validation, it's again, I would say you need to perform the experiment and do the cluster validation. Then only you can say, okay, whether the K-mean is better or C-mean clustering, fuzzy C-mean is better.
Okay, sir. Thanks.
Okay, so if there is no question, I will just move it. So now I will talk more about how we can apply this collaborative fuzzy clustering to the neural fuzzy inference network. So this is the proposed novel data-driven mechanism for neural fuzzy network. So the left-hand side, this is the original structure of the neural fuzzy inference network, and this is how we can apply the preprocessed collaborative fuzzy clustering to replace the membership value of that particular layer. So in this this neural fuzzy inference network, we have total 5 different layers. So the first layer is your input value, and then second layer is your membership function. Third layer is a rule layer. I will talk a bit more in details. And layer 4 and 5. So in the initial layers, so layer 1, 2, 3, it's called the structured learning. So when you provide your data set, so data set will first, the whole method will learn and define the structure. And once the structure has been created, and then you can use the layer 4 and 5 for the parameter learning. So layer 4 is your parameter optimization layer, and then layer 5 is the output layer, and then you can stop. So this is the how the overall neural fuzzy inference network. So what we did, we just apply the preprocessed collaborative fuzzy clustering on the given data set. So what we did, so let's say you have the given data set. So now we will divide the data set into 2 parts or many different parts. So because we don't have the other data set from the other organization, so in this case we just need to consider the original data set and divide into n number of a small data set, and consider each data set belong to the different organization, and then we can perform. So what we did, so now on the each data set, we perform the fuzzy C-mean clustering. So we compute the partition matrix prototype of that particular data set. Then we applied the collaborative mechanism, and then update the partition matrix and prototype, and then we provide those information directly to the membership layers, and then that membership layer generate the rule engine, and then we go for the parameter learning steps. Okay, so as I said, so this is your overall structure of the neural fuzzy inference system. So we have total of 5 layers. So layer 1 is your input layer. So we don't do any computation on layer 1. Again, similarly, layer 5 is your output layer. So we don't do any computation on the layer 5. So main computation is on layer 2, 3, and 4. So layer 2 is more about the membership value, where you calculate and update, and then the layer 3 is about the rule-based engine. So it's define the rules, and then in the layer 4 we do the optimization of the rules, then update to each other. So as I said, let's say this is your input value. So once you provide the input value, and this is your how the output value look like. So your input value, you have the functionality of the weight, and each weight has the and this is your input data set. It will depend on the each nodes. And then this is your association weight of the each node, and this is how your output look like. So just output is your there's nothing. This is the final output of the whole calculation. So layer 1, there is no computation, so you just provide the input data. In the layer 2, you use the compute the Gaussian membership value to compute the membership value for the given the data points. So where you need to provide some information related to the mean and the variance of the given data set, and then it will help you to compute the Gaussian membership value. So once you compute the Gaussian membership value, then in the layer 3, so layer 3 basically it's more on the fuzzy logic rules. So it's define the define the rule. So basically it's define the number of cluster based on this. So that's also called the, you can make it as a classification if you want to predict something. So it uses the AND operation as follow. So once you calculate the fuzzy logic rule, now in the rule 4, you need to update the membership, the value, whatever information you get from the layer 3. And finally, once you have, so in layer 5, you integrate the all action recommended in layer 5. And then you need to use the diffuser to diffuse that value into the one single value, and that will give you the final output of the result. So in order to evaluate the result, we use the root mean square error. So root mean square is a very commonly used when we are working with the prediction problem. So basically it's compute what is your actual value and what is your predicted value. So it's take a square root on the difference between, and then compute the distance, and then take a square root of that whole distance value. So yeah. So the first experiment we performed so we generate a data set. So it's called identification problem 1. So basically this is one of the famous time series data sets we generated, and then how we compute. So and this is your the input, and this is how your output look like. So and the input U2 is your the sine 2 pi t divided by 4, and YT is your output, and this layer contains the 3 input and the 1 output layer, and the initial value we consider y0 is equal to 0 and y1 is equal to 0 in order to generate the data set. So initially we create a set of the 100 data for the training and testing. So we generated 200 sample for the training and 200 sample for the testing. Further, what we did, we divide this 200 data sample, which one was for the training, we divide into 2 parts. So we divide the data set into 100 pattern. So each data set, let's say data set 1 and data set 2, contains the 100 the patterns. And then these are just a parameters value which we have chosen. So for the learning rate, it was 0.2, number of iteration 500, and the collaboration coefficient is 0.5. And the all result, what the result I'm going to show is based on the 30 average or mean value of the 30 different independent runs. So we run this whole program 30 times independently, and we take the average of the overall result, and this is how we perform. So based on that experiment, we compare the proposed methods with the all other existing methods on the same data set. So we can see in terms of the number of rules, okay, so we can see the proposed methods also uses the same number of rules if you're comparing the last 3 previously proposed methods. But in terms of the initial 3 methods, you can see in terms of the number of rules, is using the less number of rules. And in terms of the training RMSE, you can see it's outperformed the other 6 different methods. And in terms of the testing RMSE, you can see it's also outperformed with the other method. So you can see, yeah. So the another thing is, so this all 4 methods is used on the whole data set to train the model, but the proposed method just uses the half of the data set. So it just uses the 1 portion of the data to compute. So even you can see, even though we use the 50% of the whole data set, the proposed method is performing better in terms of. So also it reduces the computation time because we are not going to use the entire data set to train our model. We are just using the one portion of the data set to train the model. So in that case, the overall computation time has been reduced as well. And in terms of, so this is just a plot which represent the desired output and the predicted output. So the blue line is your desired one, and this one. So you can see it's almost very close with the predicted output is very close to the desired one. So that's why the RMSE value was very low. So usually we consider a smaller value of RMSE is better. And this is your just a predicted error during the method. So you can see this is just a predicted error. And so this is the result for the training one. And similarly, we can see this is your result during the prediction as well. So for the testing data as well, we can see the predicted output result is very close, almost close to the desired output, and this is just a predicted error during the testing. Again, we use another data set called identification problem 2, and then again we generate the different set of the data sets which contains the 200 data sample for the training and 200 for the testing. So again, we divide this the training data sample into two different data sets. They call data set 1 and data set 2, and perform the collaborative the pre-process collaborative fuzzy clustering, and based on that collaboration, we update the prototype and the partition matrix of each data set, and we just use only one data set to do the training of the whole model instead of using the 200 data samples. So we just use 100 data sample to train the models, and then these are the parameters we chose: the learning rate 0.2, number of iteration 300, and the collaboration coefficient 0.5. So, and then again, this whole experiment was done 30 times independent run, and then we take the average value of the whole output. And then again, you can see with this given data set also in terms of the number of rules, the proposed methods outperforms compared to the other methods, and similarly in terms of the testing RMSE. It's outperform on the other previous proposed method. So, and we can see again, so this all the previous methods uses the entire data set to train the model, but the proposed method just uses the half of the data set to train the models and get the better RMSE results. So you can see, and based on the experimental result, we can see the proposed methods is better. Yeah. Again, this is an experimental result in terms of the testing. So you can see the predicted output is very similar to the desired one, and this is your the predicted error during the testing of the given data set using the proposed methods. Again, we did further experiment on another time series dataset that's also very famous. That's called a Mackey Glass time series dataset. So this is the equation to generate the data sets, and this is your input, and this is your output, and these are the some variables, the user defined parameters, the constant value which has been adopted in order to generate this data set. So we generated around 1,000 data sample for training and 1,000 data sample for the testing. So again, Instead of using the 1000 data sample for the training, we divide this data set into two parts, data set 1 and data set 2. And each data set has just 500 samples, and we perform the pre-process collaborative fuzzy clustering and update the partition matrix and prototype, and we just use the only one data set to train the models using these parameters, where the learning rate is 0.2, number of iteration 500, and the collaboration coefficient 0.5. And again, this one was run for 10 independent runs, and we took the average value of this whole 10 independent runs. So again, we can see, just using the half of the data set to do the training, the proposed methods outperform in all aspects, in terms of the number of rows, in terms of the training RMSE, and in terms of the testing RMSE. So you can see, so we compare the proposed methods with the other existing methods. So you can see the number of rows is being used is very low compared to the other methods. And this I can see also in terms of the RMSE, training RMSE and testing RMSE, we have the lower value. That means it's a better performance of the models. So and again, this is just another way to represent what is the desired output and the predicted output. So you can see this plot represent for during the training. So you can see the predicted output is almost similar to the desired one, and this one represent just error during the training. And this graph represent the testing for during the testing. So this is your desired and the output result, and the right hand side graph represent the error rate during the testing. Yeah, so this is how we used pre-processed collaborative fuzzy clustering with the fuzzy neural inference system. Further, we apply the same techniques, which is the pre-processed collaborative fuzzy clustering, to propose a new architecture for the Mamdani and the TSK type fuzzy inference system. So the bottom flow is basically your Mamdani and TSK type fuzzy inference systems, and then we proposed the PCFC, and then how we provide the information to the knowledge base. So again, we use the data set, and then we apply separately the collaborative mechanism. Then we update the prototype and the granules, and then we provide those information to the knowledge base for the further steps for the Mamdani and TSK type fuzzy. These are the very old, but with the very famous fuzzy inference systems. So yeah, so these are the steps involved in the whole proposed method. So in the first step, we need to set the fuzzy rule using the pre-processed collaborative fuzzy clustering. Then the second step, you start with the fuzzifier. So we need to calculate the membership value. Second step is to for the inference rule engine. So we combined the fuzzified input according to the fuzzy rule in order to establish the rule strength. So again, there are some rules, and then in the fourth step, finding the consequence set of the rule by combining. So as we said, how we can update the membership value based on the given equation, and then after that you combine the consequent to get the output distribution, and then you can defuzzifying the output and for the output disturbance. So this is the whole diagram of the proposed method, how we can modify the existing Mamdani and TSK fuzzy type with the fuzzy collaborative seaming. So this is the actual fuzzy inference system, how it looks like. So as I explained, so this we have the fuzzifier, then inference rule, defuzzifier, and then output, and then you have the fuzzy knowledge base systems. So these are the very famous and very commonly used fuzzy inference systems. Yeah. So again, so this is what we did. So we propose the new system modeling for the Mamdani and TSK inference system. So you can say this is your initial input data. You divide that data set into two segments, data set 1 and data set 2. You compute the fuzzy seaming clustering individually on two different data sets and compute the prototype and partition matrix. Then you apply the pre-processed collaborative fuzzy seaming clustering on these two different value to update the prototype and partition matrix. So once you update the prototype and partition matrix, then you provide those value to the Mamdani TSK type fuzzy, and then it will give you the output. So this is the overall structure of the proposed system. So based on that proposed system, again we did different experiments. So again we use the same data set what we use for the fuzzy neural inference system. So this is just experiment for the identification problem 1. So yeah, so this is the Mamdani fuzzy inference system, the surface plot of the Mamdani fuzzy inference system on the whole data set. And then now what we did, so we divide the data set and data set 1 and data set 2. And you can see with the collaboration coefficient 0.2 when the data set collaborate, data set 1 collaborate with data set 2. So you can see, yeah. So this is the map with the this is the surface plot based on the Mamdani fish. When the dataset 1 collaborate with dataset 2 without mapping, and this is the with you can see with the mapping. So that means with the pre-processing. So you can see there are some structural changes here, which not easy to visualize, but again, in terms of if you do some validation, you will be able to see some changes here. And again, when the dataset 2 collaborate with dataset 1, we can again see there are some changes in the structure of the surface plot. So this is just a surface plot for without pre-processing, and this surface plot with the after pre-processing. And so in terms of, yeah, as I said, we can't see the result in terms of the plot. So we need to have some number to see how it's going to work. Yeah. So you can see, yeah, this table. So we calculate the training RMSE and testing RMSE with the different value of beta. So we can see this is your original genfish. So this is original Mamdani type, the fish based on which one was based on the fuzzy seaming clustering. So these are the training result, and this is a testing result. You can see after applying the proposed method, so we have the better value in terms of the RMSE and in terms of the RMSE for training and testing. So you can see the proposed methods, yeah, can perform better compared to the original genfish. So genfish is basically an inbuilt function in MATLAB. So we directly use that function to compute with the proposed methods. And again, so yeah, so this is the result when the data. So previous result was when the data set 1 collaborate with data set 2, and this is the result when data set 2 collaborate with data set 1. So you can see again there is some changes in terms of the training and testing RMSE. So the proposed methods again perform better with the different coefficient value of the collaboration. So yeah. And again, so this is another way. So before was with the Mamdani type. Now we have the second type called TSK type. So this is also very famous fuzzy inference systems. Usually if you use, if you are familiar with this inference system. So now this is the surface plot of the whole data set, and then this is a surface plot of the data set 1 when collaborated with data set 2. So the first plot is based on the it's without mapping. It's just using the collaborative one, and then the second figure, that's B, is the after the collaboration when the data set 1 collaborated with data set 2. Yeah, and again when the data set 2 collaborated with data set 1, so you can see there is a structural changes after the mapping. So you can see before mapping, and this is the after mapping. And again, this is just a detailed result for the identification problem 2 when the data set 2 collaborate with data set 1, and when the data set 1 collaborate with data set 2. So you can see, and then we computed result on the different value of the beta. So we can see for each value of the beta, I think we have the beta RMSE in terms of the training and testing compared to the original method that's called GenFIS. Again, GenFIS is the inbuilt function in the MATLAB we use, and then we compare with the our proposed method. So you can see for each and every collaboration coefficient, the proposed methods perform better with the original function, no matter whether you collaborate with dataset 1 to dataset 2 and vice versa. So for the all value of it, so you can see the proposed methods is performing better. So another thing, so these methods are based on, again, the using the whole data set, and this result is just based on the half of the data set. So again, you can see we can have the better performance. We just use the one portion of the data. And this is just a result in terms of the desired and the predicted outcome. So this is during the training, and this is during the testing when the dataset 1 collaborate with dataset 2 for beta is equal to 1. And again, this is training and testing predicted and desired result when the dataset 2 collaborate with dataset 1 with beta is equal to 0.08. Yeah, so yeah, in conclusion, yeah, so we propose the importance of the pre-processing when you do the collaborative clusterings. And also we have shown, when we use the pre-process collaborative clustering with the other existing techniques such as the neural fuzzy inference network or Mamdani or TSK type fuzzy inference system. So we can see the new proposed methods. It's performing better. So it's not only performing better, it's just also based on just in terms of the computation time, although I didn't show the computation time here. So although in terms of the computation time, the proposed method is faster than these all existing methods, because the only reason is using the less number of rules, as well as is using the small portion of the data set, not using the whole data set. So I think there are if you guys are keen to work in this research direction, you can directly use these techniques wherever apply to, and then you can probably see how it's going to work. So the only problem at this stage because the value of beta is a user defined, so we don't know what value of beta is suitable for whole data set. So further, we are working on the optimization of the optimization of the collaborative coefficient. That's a beta, the value of the beta. So of course we can use a different optimization technique, such as the PSO or D or ZD and so on. So this is a future work which we are going to work on that part. But of course, there are lots of scope. You can directly use these techniques, wherever fuzzy C-mean supply, you can just replace with the preprocess things. Again, instead of using the whole data set, you can just use the small portion of data set to train your models, and it's going to work. Yeah, so I think that's all for today's presentation, and I welcome your questions if there is any questions which we can discuss.
Yes, participants. Yeah, thank you so much, Dr. Mukesh Prasad. If there is any question from the participants, you can raise the questions here. Any questions? Actually, this thing is that, sir, the FCM is a quite high level for them. They don't know the fuzzy theory
Yeah.
as well. So that may be the reason that they are not having any questions. Anyways, thank you so much once again, Dr. Mukesh Prasad, sir. Now I request Achit to please give
Yes, ma'am.
Thanksgiving on the behalf of DST Sense ACM BHU student chapter.
Yes, ma'am. Am I audible, ma'am?
Yes, you are audible.
Thank you, ma'am. Good evening, everyone. It is such an honor for me to get the opportunity to thank you all personage. On the behalf of DSTCM's BHU ACM student chapter, I, H. Katyar, would like to express my gratitude to all esteemed delegates of the webinar for this presence and contribution to make this webinar a great success. I extend my gratitude to our honorable guest, Dr. Mukesh Prasad, to take out time from his busy schedule to grace the event. Thank you for inspiring and encouraging us with your words on this special day. I must thank the organizing team, volunteers for working hard for the past few days to make this webinar successful. I congratulate all the participants for their active participations. Thank you everyone once again for making it a great success. Thank you so much.
And again, thank you, Dr. Jyoti, for giving me opportunity to discuss my research work, and to the students and the other participants. If any of you are interested to do some research in the area of machine learning and artificial intelligence, so you guys feel free to approach me. So I can guide you to do some research in turn, either during the summer or winter. So we have some topics, and I'm looking for some students to work on those topics remotely during the winter or summer vacation. So feel free to reach out to me. Yeah.
Thank you, Dr. Mukesh. So it's a nice opportunity for all of you. These are the students of our department, sir. So I would request all of these, please go ahead with the suggestion of Dr. Mukesh Prasad, sir, and go ahead and do some research with him in machine learning. Thank you so much once again. It was an honor to have you here with this event of the DST's BHU ACM Students Chapter, sir. And we would ask you to have further more sessions in this area if you have time further. So
Yeah,
we
if I knew before, like they are just undergraduate or postgraduate
they are
students.
PG students only.
Yeah, so I would have prepared some basic things, more on the application side rather than the research side, so they can get more excited to do some research. Anyways, maybe in next time, whenever I get opportunities, I will talk some very basic things and give you some ideas how you can apply the machine learning, artificial intelligence, or data analytics into many different areas. So
Sure,
I
sir.
think you guys will
We
be
will
more.
definitely have a day-long workshops if you like and you have time. So we'll plan that accordingly.
Yeah, sure.
Yes, thank you so much once again. Now I request the participants to please fill in the feedback form as given in the chat box, and I request all the participants and thank you all the participants for being here till this time. Thank you once again. Thank you so much, sir.
Thank you all. Take care. Have a good day. Bye.
Same to you.
Yeah, thank you, sir. Thank you, ma'am.
Thank you, sir. Thank you,
Thank you,
ma'am.
sir. Thank you, madam.